So this is our Sunday paper reading. We are going to discuss this paper, BERT, Pre-Training of Deep Bidirectional Transformers for Language Understanding. BERT has become perhaps the most used model in natural language processing. There are many variations of it that have come up over time. And more and more work is still being done. Now, this is a large model. Quite often, you can take this model and just apply it to your task. It has been designed in such a way that it's very, very easy to apply it to a wide variety of natural language processing tasks. We saw that in the lab, if you recall, in the lab that we did on Wednesday, we used the Hugging Faces transformer library, and quite a few of them were BERT-based transformers, and we used it for quite a few tasks. So BERT represents actually quite an interesting point in the development of transformers or the use of transformers for natural language processing. If you recall, in the previous Sunday, we talked about attention is all you need. When we talked about attention is all you need, we talked about the classic transformer architecture that is mentioned in that paper, which had the encoder and the decoder part. So I will start by just reviewing that in a very, very quick way. I won't get into the details, it's just keep it to a high level so that we can focus our time today to this paper. So what was attention about? The attention is all you need. If you recall, it talked about something called the attention heads, which could pay self-attention between words in the sentence. One word could pay attention to other words in the sentence. So what was it made up of? An attention head was made up of a set of a few layers of attention, right? Or self-attention, if you wish. Self-attention. And then there were multi-heads. The encoder was built from many heads. And likewise the decoder, also the decoder was made out of many heads. So they should become were made out of many heads. And this is how it looked. The encoder, so one encoder layer was like this. Basically what you had is you had a situation where you could take, suppose this is your attention block. You would get the words. So suppose you get a word, the cow jumped over the moon. So you have multiple words. I will call this W1, W2, W3, W4, W5, W6, and maybe full stop, W end. Right? And so all the 7 words, they would go through a few transformations. What the first thing that would happen to each word is that it would go through the embedding. It would get converted to word embedding. So let me call it E1, right? And this word embedding is it's actually built out of 2 things. It was built out of the little E1, let me call it, little E2, little E3, little E4, E5, or maybe I'll use capital, doesn't matter, E6, E7 of sorts, or E end, right? And then what you do is you couple this layer with the position embedding of each of these words, right? You take the position embedding, P1, the position embedding came from just specifying where in the sentence it is, P4, and P5, and so on and so forth, P6. B7, right? And these together, you treat it as let me call it the big embedding vector together, right? Is the complete encoding of the word and its context, its position in the sentence. Are we together, guys? Right? And here we go. E1, E2, E3, E4, E5, E6, E7. Now, the interesting thing that this did is it would break up each of the words into a K, like think of it primarily as a K, how should I say it, three individual pieces, a K, V, and Q. Each of these words would become K, V, Q. K, V, Q. Three different vectors. If you remember, these were in the original, if I remember it right, it was 64 dimensional vectors, right? A K, Q, a K, Q, Q, and V. Today I'm being particularly clumsy. 64 dim vectors, whereas the encoding started out with a fairly high dimensional. Even if you take a 512 dimensional encoding and 512 dimensions for the position encoding, the word encoding and the word position encoding, what you fed in was actually a pretty big vector, 1024 dim, if I remember right, from the original paper. That is what you would feed into. And then what the attention block would do is that it would generate KQV. And now, so 1, 2, 1, 1, 1, then this would be K2, QV2, sorry, Q2, V2, K2, and so forth, right? So this is your Q7, V7, and K7, right? And now the point was that which word was paying attention to which other word. And the crux of that was, we were saying that the attention that a query word QI has, let's find out how much attention it is paying to each of the other words. So let's mark each of the other words as K, J. You take the dot product of these two and then scale it the standard decay, but we can ignore the scaling part. So then what happens is you will end up with a bunch of dot product numbers. And when you softmaxes, what will it do? It will convert these into, so let's go step by step. You compute this, you get a bunch of, this gives you a bunch of energies, an array of energies, right, for QI. And then what do you do at that particular moment? What you have is these energies, you softmax. Remember, we talked about softmax. So when you softmax this QI, KJ, DK, what happens with this is now you get probabilities. We get an array of probabilities. And this is sort of, roughly speaking, the measure of your attention. And then when you multiply this with VJ, so the attention, the full attention step after this, if you say from here to here, and then finally the attention was just going back to the definition of attention. It was quite straightforward. Attention that QI is paying to each of the other words in the system is this VJ, that to the word J, it is paying this much attention. This is the intuition behind that, right? This is just a norm, just to prevent the gradients from blowing up and so forth. So this is times this. Right? Usually people write the VJ on the other side, but I wrote it here. So this is a recap of what an attention is. It just helps a word in a sentence decide or figure out which other words to pay attention to and to what extent. So it may say that, for example, it may so happen that, let's say, VI is equal to 3, right? So then the attention that the third word pays is maybe, let us say that this thing may come out to be for the first word, second, third, fourth, fifth, sixth, seventh. So it may so turn out that this may be small, this may be even smaller, this may be this. Then it may just so happen that this it is paying a lot of attention to. And maybe to this word it's paying a little bit of attention to. And that's about it, right? So it distributes its attention, distributes its attention over other words in the sentence uh, in an intelligent way over the sentence over what did I say? It says over other words in the sentence in an intelligent manner. Right? And that is the gist of it. If you know that these two words should pay attention to each other, you can feed in fairly long sequences, relatively speaking, and not fear what problems that we had with recurrent neural networks. Namely, you feed everything sequentially, and the thought vector or the context vector begins to forget what is it that was there in the beginning of this sentence, right? So if you remember the RNNs, they had the characteristics of the character Dory in Finding Nemo. It tends to forget early stuff pretty quickly. So this is our attention. And now what we have is the rest of it is straightforward. You have many attention layers. A classic transformer, if I may say, classic. I don't know if it is appropriate to use the word classic, but I'll use it because it is all just 2-3 years old. It's also new, all of these ideas. But this was, and I will gloss over a lot of the details. It had an encoder-decoder block, right? This is the encoder block, which is encoder. Let me write it on the side. Encoder. It was, you feed in the word or word embeddings, the word, and I will forget the word. I'll just put it in. You go through the whole process of creating the embedding vector that we just talked about, E2 and so forth. In this case, 7, let's say, 7 words. Or let me just say EN words that make up the sentence. So they are going in here. And then what happens is that you have not one, so you have multi-heads. So first thing is that there are multiple heads sitting there. One head is looking at one aspect of the language, another head is hopefully looking at something completely different in the language. But each of the heads is made up of, each head has many layers, many attention units layered on top of each other. So the output of one goes into the input of the other. Right? So there was this whole business. And of course, there is one more, I forgot. There is a softmax. There's sort of a ReLU layer to introduce the feed-forward layer, to introduce the non-linearities into the transformation so that it can actually capture things. So, but I will just write it down. Now, the classic transformer had about, if I am right, 6 layers, no particular reason it was 6, and there were essentially 8 multi-heads, if you recall, right? But those are small details, and there were some feed-forward, there was a layer norm, then feed forwards, and then finally some more weight multiplication. And then the output of this, and I'll change the diagram a little bit. The output of this went into the decoder layer. And if you remember, the decoder, as we talked about in the classic paper, is, and that's important to remember, what were we giving here? Let us say that this is E, and suppose you're translating from English to French. So let me just use the French 1, French 2. And let's say you have gone to 3 French words so far. The rest of them are masked. Isn't it? They become minus infinity values because these are all floating point numbers, right, ultimately. So what you do is, suppose you have decoded 3 words. You have produced here F1, F2, F3, and your task is to figure out what is F4. What is the 4th French word? right, sequentially. So your decoding is happening here, like this. And when it happens here, it takes two kinds of things in as an input. The F1, F2, F3, they first go through their own, the same cycle that they go through here, and the output comes and it merges with this output coming here, and it goes finally to another decoding block, the real decoding block, a part of it, which is essentially the same as the encoder, but those are technical details, and then it produces these things, right? Do we remember this part, guys? This is your basic classic transformer, if you review that. It is all right. It's a complicated architecture. It is possible that you may not, it will take a little bit of time to remember this. It is worth remembering this because in the NLP community, it's a sort of a celebrated diagram of the classic transformer. And it helps to know this. It facilitates conversation. For example, this particular discussion on BERT is informed by this classical transformer in many ways. So we'll talk
Asif,
about, yes, please go ahead.
sorry, you last time you mentioned earlier, but it was a little bit short of which part of this in the transformer is parallelizable? How can you parallel the
Oh, that's
work?
the whole thing. Very, very good. See, the parallelism comes from this. First of all, the entire sentence one, goes in at once. In fact, it is necessary. You can't feed it sequentially. Unless you give it all the words, how will one word pay attention to another word? You see that, right? So you have to parallelize it. That is one aspect of the parallelization. The other aspect is you send in not one word, but one sentence, but you can send sentences in parallel, a batch of sentences, a batch of sentences can go in parallelly. Did I? Parallelly. I don't think there's a double L. Parallel. Come on, correct me with my English. Is there a double L? Why? I suppose so. Or maybe I misspelled
Say
it.
parallel.
And so word parallelization. So words parallelization. Token parallelization. This is so tokens are going in parallel. Token parallelization.
So as if in the first instance, the entire sentence goes in all at once, and then each word is being processed like with respect to the other words in that sentence. So the parallelization is happening from the word level, right?
Yes, exactly. And the other aspect is if you think about it, you can actually feed this transformer different sentences so long as you tell it that this is one entire sentence, this is your sequence, right? You can feed in many sequences in parallel because what it does with one sequence is a whole lot of matrix multiplication and activations and so forth, and it can in parallel do it with many sentences, right? And that is a beautiful thing. That's what makes this transformer so powerful. For example, you can feed in 2,000 sentences at one go if you want. It's a big tensor. You better have good GPU or TPU or a memory to be able to feed that much, right? But at least you can feed it in small batches.
So, as if in this context, when you say parallel, if I were to translate that to what we see there right now in terms of there's W1 through to, let's say, you've written it for WN. So there
Yeah.
will be W1 through to WI, which is one sentence. WI plus 1 through to WJ would be second sentence, and so on. All those sentences are laid one next to each other.
No, no,
That's
no.
what we're
It's
calling
not
as
like that.
parallel.
It's not like that. So think of one sequence as one sentence. Sentence. One sentence. Now I'll qualify this word in sentence. So sentence may be the English sentence, or it could be any sentence. Definition is any logical unit, any logical set of sequential words right? So if you so choose, maybe a paragraph is your sentence, who knows, right? So now what you do is one, but let's stick to the common English definition of sentence to keep it obvious. So what happens is one sequence is like this. Let me call this E of the first sentence, E1, E2 of the second sentence, E3, sorry, of the first sentence, sorry, I shouldn't mix it. This is the first sentence, 1, 1, all the way E1 of the, so suppose, nth. And in the, what you do is you find the longest sequence of sentence, the longest sentence that you have. Let's say your longest sentence that you have is 20. Then what you do is you make sure that all the sequences are of length 20, and if needed, you pad them with empty tokens in the end. So sentence 1, right? So this is your sentence 1. And now suppose you have sentence 2. So it will again be E2, 1, all the way to the En, right? So now what happens is, if you really think about it, you can feed this in one go into the transformer, right? Isn't it?
Mm-hmm.
Especially the encoder. You can feed this entirely into the encoder. And then, because this sentence is completely independent of this, right? You can feed this also into the encoder, right? Into the same encoder, but it will just take a parallel path. This will not influence this. In other words, the computation that's happening with the first sentence will not affect or be informed by the computations that's happening in the second sentence, right? It again can go in parallel blocks, and so on and so forth. So suppose you have sentence K, then you can have EK1. Now, why is this a big deal? Like, why do we make such a big deal about this? And let me just use the word, instead of encoder, let me use the word transformer here, the whole transformer, TR. So they can all be fed into the transformer in parallel. And that's what you do actually. You decide how much space you have, memory you have during inference time. Based on that, you don't just send one sentence at a time. You take a batch of sentences and you keep feeding it in. Right? So this is what you have. So now to contrast this, think about the RNN. So in contrast, RNNs were what? They were basic units. You would feed in word 1, H0 would produce H1, hidden state 1 would again need word 2, H3, word 3. And so you would finally get a context vector, right? Context or H final, or the context, or what I call the thought vector, capturing the essence or the concept that has been that is there in the sentence. So what happens is RNNs and the gated RNNs, LSTMs also, which are just gated TMs, GRU. They're just things that forget about feeding a lot of sentences. They just work one word at a time, isn't it? So they are not massively parallelizable. That is one limitation. The other limitation with them is they are not conducive to transfer learning. They're not very conducive to transfer learning. So the whole idea is that if you look at the image processing world, remember in the very first lab we wanted to do some image classification. We wanted to classify our own images, cats and dogs and whatnot. And we just took a pre-trained model, a VGG, ResNet 10, I believe 106 or something like that, and Inception and so forth. And we just directly applied it to our data. We did not even have to fine tune it. That is remarkable because these models take a very long time to train. And if you could just use and apply it, or just do the last mile, a little bit of fine tuning of the model in the very end and get your work done, that is a gold standard. You ideally want that. You don't want to teach the neural network from scratch. It is something like that, when you hire if I were to take a more social analogy, if you hire an employee into your company, you know that the employee doesn't know the specific code base or the projects in your specific domain to as much detail as the employees do, the existing employees do. But your hope from the candidate is that candidate is at least pre-trained to the level of having an engineering degree, right, and knows most of the concepts of engineering or computer science, so that you have to just do a last line training or fine tuning of the person to make the person productive in your workplace. That is taking an analogy from our real life. Would you want to do that, right? You wouldn't want to start every time you want to hire an employee. You wouldn't want to say, all right, let me start from a kindergarten level education and put this person through another sort of a 17 years of education before he can start being productive in this team. That would be insanity, isn't it? And nobody does that. So a very similar thing is there in deep learning, that for many, many tasks, we ask, can we not just use transfer learning? Can we not just take a model and fine tune it if needed? No. It is like training the new hire, just putting them through an orientation process, teaching them a little bit of training, and they're ready to go. They're ready to be productive. That's one way to look at it. So that is the gold standard. So those things with RNN, RNN-based architectures, they are a little hard. So the two limitations are they are very sequential, and the second is they are not conducive to transfer learning. And the third is, of course, sequentiality not only means that they are slow and not very parallelizable. The other problem with sequentiality is they have the characteristic of Dory in Finding Nemo. In other words, they tend to forget things. If you tell them a very long story, they'll forget the first half of the story, pretty much. Right? This sort of putting it very uh, sort of is oversimplified way, but that's that, right? So in contrast, if you think in this, so when you contrast that with, so let me write those limitations, RNN's limitations, just as a review: slow, owing to being sequential, B, the second limitation that they face is they are can't handle long sequences well. Forget the early parts. Forget the earlier parts. So forget or fade the earlier parts, if I may use, not quite forget, but fade the earlier parts. That's a limitation. You see that, right? And see, it's not conducive, not very conducive to transfer learning. Right? And these are huge limitation. And in some sense, when BERT came about, this architecture came about here, and not BERT, the transfer architecture came about. So let's now contrast it. Will it be slow? No, you can feed all these sentences. First of all, you can feed an entire sentence at one go. And not only that, because sentences are independently processed, you can feed the sentences together in a mini batch or a batch or something like that. Now, in fact, it is the opposite. You can't feed it word by word. You have to feed it sort of the whole sentence so that it can do self-attention on it. So that is one great advantage. Like when you contrast that with transformers, you realize that transformers, right, have the advantage that they're very fast, right, because of parallelization. Right? So you can actually use the GPU, the hardware, utilize the hardware efficiently. The second thing is B. It is it handles long sequences better. There's still scope for improvement. Sequences much better. And the C is very conducive, quite conducive, rather conducive transfer learning. So this is the RNN limitations. So does this summarize it for you guys? Why transformers are quite a breakthrough actually.
As if a follow-up question.
Mhm.
So when you said we put in a sentence, so it enters as a batch, and it computes all the energies of the word in that sentence in
No,
parallel.
a sentence is not a batch, Patrick. You don't use the word batch as a sentence. You use that you send the whole sentence as an array of words, array of tokens.
Right, right. Yes, I meant an array. So we send it in as an array, and it computes the energies of the words within that array. Correct, Asif?
That's right. It basically computes the self attention within the sentence. Who is paying attention to what?
Right. So my follow-up question is: if I put in a second array, like a sentence number two, it also pay attention to the previous one?
No,
Let's
that is
say,
the whole point. The classic transformer, no. The classic transformer has no recollection of the previous sentence at all. It is completely independent.
so if it processes it in parallel, it just treats each sentence independently still.
Yeah, independently. And that's the reason it's able to process sentences in parallel. Because suppose it had to do cross sentence context or cross sentence attention, then that would be a completely different ball game, isn't it? Right. So it doesn't do that, at least in the original version. Um, so you just think of it that one entire sentence goes, and it just so happens that the architecture is such that because everything is done at the level of a sentence, all that self-attention business. Therefore, the next sentence or the previous sentence, it is completely unaware of what went before and what went after or what is going in parallel.
Okay, understood. Thank
That
you.
is the big point.
So Asif,
Mhm.
so what about randomness? So how do we achieve randomness here? Because we are saying that like not like in transfer, not in the transformer, but in general, anytime we are like feeding the information, we want to randomize or we want to have the random state equal to true. So does that concept apply here?
Yes, it does. When we get into BERT, I'll specifically show what mischief we do in training the BERT.
Okay.
Randomness will come in. So, all right, guys. So this is the context. This is what we know so far. Are we together? So the basic lesson is that RNNs are in general not as powerful. So if you look at the prior work being mentioned in this paper, so now let's start reading the paper from the beginning. All right, guys. So just as again, I'll just scan through what we talked. Attention is all you need. It introduced the classic transformer and the concept of self-attention, in which you would take the word encoded by position and embedding, or feed it into the attention block, and you would get the Q1V, the QKV, the query value and key vectors, the 64 dimensional. Right? And in a way, you notice that they're smaller dimensional compared to the input 1024 dimensional input typically. Then we have the concept of attention. If you ask this word, a word QI, what is it paying attention to? So what you do is you take the QI and you do its dot product with all the keys, all the other keys, the other words keys. So it will be near some other word in the key space, the query vector. And when you see that this query vector is close to some key, some words key, you say that it is going to pay attention to that word. And so what you do is you softmax the energies that you get, how much attention, and then you multiply it by the actual value of that word that has also gotten computed in the process. So your net result is, after this little bit of mathematics, simple mathematics, you get what is called the attention. And so you'll see that attention, Q3 seems to be paying a lot of attention to 1, 2, 3, 4, 5, 6, 7, the sixth word, and a little and quite a bit of attention to the sixth word, and a little bit of attention to the fourth word, and so forth, and not much attention to the rest of the word. So that is the point about attention. It led to the classic transformer architecture, which is the well celebrated architecture. It has multiple heads of and this encoder blocks, or the sort of attention block, sorry, and each attention block has internally many layers of the attention, attention. Each sort of attention head has about, I think in the classic architecture, 6 layers of attention blocks. Each attention block does that. It splits the word that is coming into the KVQ space, right? Vectors, and then the rest of it is, we talked about it. In contrast, so if you think about it, why is that such a great thing? Because transformers can parallelize at the level of the word, and then because the sentences are independently processed, then even there too there's parallelism. In contrast, an RNN used to have the following limitations. They were slow because you had to feed in words sequentially. They couldn't handle long sequences well. They forgot the earlier parts, or the earlier parts, they begins to get muted or faded out in the thought vector, in the context vector. And it's not quite terribly conducive to transfer learning. So, it almost seemed, relative to the breakthroughs that were rapidly happening in computer vision, it seemed to be behind the times, basically, till the transformers came about. So these are big things, to be able to use transfer learning, to be able to parallelize and do the computations fast. Right? And so in contrast, the transformers are very fast. Right? Their processing speed is just lightning fast. They handle long sequences much better. Right? I wouldn't say that they handle it very perfectly. There's still limitations, but they do a much better job than the RNNs do. And they are rather conducive to transfer learning. In fact, there's a whole, today, most of the time, you just take an existing transformer and utilize it for your purpose. So it brought about a sea change in the field. And it sort of had the same, people said that it was like the 2014 movement. In 2014, CNNs, or computer vision, had a deep learning for CNN, so it's sort of deep learning. It had a breakthrough. It was really when everybody began to pay attention to it. It was breaking all records, the ResNet and the VGG and all of that. And they were like really showing astounding results. So in many ways, the transformers in 2018, transformer paper original came out in December 2017. 2018 was the similar moment in NLP world. And so what we are going to do now is walk through a very, very popular implementation of this. But before I go into that, we agree that our RNN-based implementation is likely to be underperforming. So this thing talks about 2 architectures. One is ELMO, which is a bidirectional. Sort of RNN. It uses LSTM, the more modified, the gated with the forget and the remember gates, if you remember, that version bidirectional using LSTMs. Yeah. So it is RNN technology. So you can imagine that what it does is, if you have to predict some word here, and you have W1, W2, W3, W4 is missing, W5, W6. You have to predict this word, WN. What you have to do is, you could go in this direction. One RNN would take this word, this word, this word, and then it will ask this question, next word, right? And then you could do the other way around. You could take this word, then this word, the second word, will be this, this, this. And now you ask once again, what is the next in the backwards direction, right? And you use both of them independently. So you have a forward network, you have a backward network, and somehow you train them together, backward network, you train them together to nicely be able to tell what word stands in between, right? So that was the state of the art. Then came important sort of a thing. It came the GPT-2, sorry, not the GPT-2, the OpenAI came up with the GPT model. What the GPT model is, it said something quite interesting about the transformer. It says, let's go back to the transformer. And so now pay attention to this. So it said, let's pay attention only to this part. If you really look at it, as word after word after word, F1, F2, F3, let's say the French words keep coming out, they go back and become input to this decoder, right? And the thought vector has, I mean, the encoded message is already just sitting there being incorporated. But see, what is happening in reality is this is predicting the next word. It's a forward direction from left to right. F1, right, leads to F2, leads to F3, leads to F4, prediction of the F4, right? So suppose you have these three words in place, you can predict what F4 will be, right? That is what the decoder does. And the GPT architecture, it basically said that let us let us do one thing. What RNNs were doing, we will do it with the transformer, but we will forget about the encoder part. We'll only use the decoder part. So when you only use the decoder part, let me highlight this with a thicker line. This is when you just use this and you say, forget the encoder part in some sense, and just use this, we can get away with it. You treat it the way you would treat an RNN, sequentially produced, but make sure that we use attention, right? Attention heads, not the traditional RNN heads, right? So then this is your GPT model, right? This focuses on that. So that was the other state of the art. The good thing with GPT was it was attention based, right? So let us realize, so it was transformer based, whereas Elmo was LSTM based. These two existed, and they were doing quite well actually. The glue scores, so one of the benchmarks by which you can compare, and a pretty important benchmark is something called glue. Just think of it as a measure, a bragging rights. So if you look at this, and I'll try to highlight a few sentences here. Okay, look here. If you look at OpenGPT, the scores, the scores that you are getting is 75. Sorry, let me highlight it because red we kept for this. Do you see 75 here? That was what the GPT was coming up with, isn't it? And what was Elmo doing? Elmo was not doing particularly bad. It was at 71, right? So I'll write those numbers down, 71, 75. And then came the BERT, right? And since BERT has, in this case, they made two models. One, just to show that the fundamental architecture is superior, they used the same number of sort of the same size neural network as GPT. And they called it the BERT base, one version. Then they used another version which had a lot more layers, like at any one head, the attention head, it just put in many more layers, I believe 16 layers or something like that, and or 12 layers. We'll see what it is. Somewhere in here is the detail. And then they also increased the number of heads. The multi-head had many more heads. And then they went with that. That was the BERT large. And you can clearly see that BERT large is 82 points. So this number, if you look at it, I'll just maybe mark it in green. if you look at this number, 82.1, so it suddenly made, this much point jump is a huge jump, right? So it made quite a huge jump from the state of the art. So you'll often see the word SOTA written in these papers, SOTA. SOTA stands for state of the art. I'm mentioning it because someone asked me. So you clearly see that it begins to do that. So now, what does it do and how is it implemented? Let's go and study the paper and then I'll explain that. But just to give you a preview, what they did is they said, they took the opposite approach. They said, forget about the decoder. We will only take the encoder. This is what BERT is made up of. It's a very surprising idea. It is saying you can do pretty good transformer by taking only the encoder half of the transformer. See, when you look at the GPT part, it sort of makes intuitive sense. You are saying the previous words that have been, let's say that you're doing machine translations, the previous words in French that have come so far, they form the context of the next word that you will predict, right? Along with obviously the original words, the original English words and so forth. So together you can feed it all into, forget about the encoding, you can sort of feed it all right here, the English also. So then you'll get your translation right away. Right? So your vector, your input vector is sort of the words of English and the words of French and all in one go, and forget about the encoder. Whereas a BERT takes the opposite approach. It says, forget about the decoder, we'll just deal with the encoder. So how does it work? How in the world can it work? Let's go figure it out. Right? So in this, I will start reading this paper from the, give me a moment. I'll start reading it from the beginning. The most important thing that they say here is in the very first line, they say that unlike recent representation models, BERT is designed to pre-train deep bidirectional representations. And so the most important things that it says, I guess, what should I do here? More colors or yellow. Where is the highlighter? I'm just looking for a highlighter here. No, it won't let me do that. Okay, this tool has a issue. Maybe I can change one of them into a highlighter. Can I do that? More colors. No.
Highlighter is your first one, Asif.
On the left here?
Yeah.
That's an eraser.
Oh, okay.
That's an eraser. It's all right. I will sort of let it be. I'll just use yellow to highlight it. So the sentence that we are paying attention to.
Highlight is your fifth one.
Oh, right. Thank you. I did set it up. Yeah, that's what I thought I had it. So there we go. So this is the crucial sentence. A BERT is designed to pre-train deep bidirectional representation by jointly conditioning on both the left and in all layers. So let's focus on that. A lot is packed in there. First, it is saying that you can use pre-trained, like you can use it for transfer learning, right? You can pre-train a BERT model and then use it in different contexts for other purposes. Right? That is one. And the second thing that it manages to say in just one short sentence is, it is conditioned on, or a very sort of a oversimplified version would be, it has learned from both right and left context. In other words, the words that are before that word, if you take a word in the sentence, imagine that you're trying to either predict the word or do something. So it has learned from the words that come before and the words that come after, right? Somewhat like Elmo, except that the Elmo, the bidirectional, is using two effectively independent RNNs. Right, one trained to move from left to right, the other trained to walk backwards from right to left in English. Right? So this one says that you can literally jointly condition on both left and right context in all layers. That sounds quite interesting, and we'll see how. So then they go on to say the consequence of it. As a result, the pre-trained BERT model can be fine-tuned with just one additional input layer. So suppose you're writing a classifier. If we imagine that you're doing sentiment analysis. Right? So what they're saying is once you have a pre-trained BERT, all you need to do is to make it into a classifier, what do? Roughly speaking, you realize that you take some form of output from BERT, right? A hidden state from BERT that it produces, and then feed it into a softmax layer, isn't it? Or a sigmoid or whatever you want. And now you got a sentiment classifier. Am I making sense, guys?
Asif, when you said you take a hidden layer, are we introducing one or are we just
No. Whatever. So think of the hidden layer as whatever comes out of the transformer.
Oh, okay.
So the basic idea is this. Suppose you want to take a transformer. Let's say that this BERT transformer, you give it an input, and the reason you call it hidden is because whatever BERT produces is not what the final state is. All you need to do is put it through a softmax, a classic logistic regression. You remember your basic logistic regression, right? And then right away it is producing the sentiment, and the output would be the output of this would be positive or negative sentiment. Right? So to the extent, see, hidden layer, we always use the word when it is not the final output. So the BERT's output, so therefore, by definition is the hidden layer when you use it for some other purpose. Are you understanding that now? Yeah, so the output of the BERT is basically feeding into something downstream. And people use the word downstream, whatever task you want to do, downstream task. And that speaks to the generality of it. Actually, one of the most amazing things is that BERT, when this paper came out, and in the very first version of it, a single BERT, same architecture, trained with 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 all the weights there and needing just some fine tuning. What does fine tuning mean? Once you have trained the BERT using, so you have to pre-train the BERT. The steps are you go number one, pre-train. Pre-train. This is the hard part. Go pre-train on a large corpus of documents. And so once you pre-train, you get a BERT which is ready to be used. Number two, what you do is now BERT will have gazillions of parameters, right? The base model, I believe, has 140 million parameters or something like that. The BERT large, I believe, has close to half a billion parameters. Right? But those parameters, what you do is they almost, for whatever task you do, you don't have to shake them up a lot. They just need to be fine-tuned to your problem. So what happens is when you jointly train this BERT with where the weights are already close to the right answer with respect to your problem, what is happening is that some weights here are getting trained, right? The standard logistic regression weights are getting trained. And when you backprop, maybe the parameters that are there in the BERT model, they will go through some tweaking, some fine tuning, some little changes with the gradient descent. But very quickly, you'll be able to train it. Right? And in this paper, they make it a point. They say that, that if you use it for all these tasks and a whole variety of tasks they speak of. Actually, let's jump ahead and look at the bragging rights here. So if you look at this here, this table, these are all different things. Sentiment analysis, question answer, the question answering, 1, 2, 3, 4, 5, 6, 7, 8. So 8 different tasks. If you look at 8 different kinds of tasks, one of them is basic things, ablation. So if I give you 2 sentences, can you tell if the second sentence should actually follow the first, right? But there is a relationship between that is sort of the entailment, sorry, not ablation, I apologize, entailment, that it is really should be the one following it, or is it some random sentence, things like that. So that is it. There are 8 different tasks. And if you look carefully in all 8 different tasks, this seems to have, like, if you pay attention to this guy here, do you notice that this seems to be beating all the previous, if you just compare it to this, compare it to the existing state of the art, do you see how much improvement there is everywhere? And what they are saying is that once you have trained, pre-trained BERT, then from a pre-trained BERT to go to these tasks, putting a head layer, either a classifier layer or something like that, and training it, you can train these all within 1 hour, right? So that is the power of transfer learning that I was talking about. Once you have a fully trained BERT, you just apply it to your specific domain, do a last fine tuning on your hardware, and on any reasonable hardware, like a single workstation hardware, you can finish the entire training within an hour. Right? And so this has become this is the power of it. Like that's why it's so practical, and it just took the world by storm in our little corner of NLP world. Does that answer your question? So now so it goes on to say this point very well. As a result, the pre-trained BERT model can be fine-tuned with just one additional output layer for whatever task you're doing to create state-of-the-art models for a wide range of tasks. So it's surprising how versatile transformers are. In fact, just about every area of NLP seems to be benefiting from the transformers. And so with that thing there, we have a situation where you have the same level of pluggability that you had for like in the world of computer vision. The other important thing that it says, and so it says all sorts of tasks, right? For a wide variety of tasks such as question answering, language inference, etc., etc. And the more important thing is for each of these tasks, before BERT came about, people had custom architectures for each task. So if you were doing question answering, you had an architecture that worked best for question answering. You couldn't apply the same architecture to sentiment analysis, right? And things like that. So there was literally you need one solution, fine-tuned and specially trained for one purpose, right? But BERT came, and as I said, its crown achievement was that in one fell swoop, it gave you an architecture that pretty much became the state of the art in many, many tasks, 8 tasks at least. Yeah. So we'll learn about that in a moment. So now this language, pretty much I've explained it to you. So here is one word in this paper that is crucial. So you can read this and you will realize that the rest of the things is what I have been talking about. And so one of the nice things is you can pre-train all the parameters, when you're doing the fine tuning, you can actually fine tune all the parameters, not just the last few layers. It works just as well, because there's only a little bit of a tweaking. So in a few epochs, you're done. Now, in this paper, they introduce this BERT. This is where they define the word BERT, right? And it goes on to say that it does it. And the trick that it does is it uses an old idea. It is called the closed task. Looking at the date 1953, it is probably a concept that has existed in natural language processing for almost 70 years. Right, closed task. What is the closed task? It is basically this, roughly speaking, that if you take a sentence, A, B, C, D, E, F, G. Let us say this is these are the words in the sentence. So suppose I go and hide this D. I mask it, and I ask you to tell me what word it was that I hid from you. Right. So the models that can do that, they are masked language models. Right? And we talk about that masked language model. So they coined this term. A lot of the literature there is interchangeably people use the closed task or MLM when people talk about it. And we will use this as they use this as one of the 2 techniques. So let's see what is the technique that they actually use. Now, I talked about the prior work before BERT, Elmo, and GPT. I won't talk more about it. So let's go and see what BERT does. So look at the BERT architecture. First of all, it says that it uses the famous attention is all you need. Remember, this paper, Vaswani, is the attention is all you need paper, right? And it says go read. It is all, so it says that the implementation is almost identical to the original, right? The transformer, almost, with the difference that you don't need all aspects of it. So this is it, and we denote the number of layers as this. We primarily report results with two models. So look at the BERT large, pretty big, isn't it? So the number of hidden layers, sort of the number of layers in a transformer block, just one block of transformer is, or one head is 12 or 14 or 24, my goodness, 24. In each of these, the number of, what is it, attention. So how many attention heads are there? You're using 16 attention heads. So it is like attention heads have practically doubled, and the number of those attentions inside each head is almost become six times four times, pretty large. So it leads to the total number of parameters, which is 340 million. And the hidden state that this BERT produces is 1024, a vector of a 1024 dimension. So that's a pretty large vector that it produces. The base version of BERT produces 768. So when you do the lab, what will happen is you try to train or even fine tune BERT large. It takes a little bit of time. It can take an hour. So people, when they're just experimenting, they start with the BERT base. They see good positive results, and then they move on to BERT large. That's one way of looking at it. Right? So this is that. Now comes the input-output representation, and this needs some bit of explanation. The way it deals with is the inputs are actually not words. And the reason for that is there was an interesting finding a few years before this paper, which was the work of the word piece embeddings. People found, so let me just put it this way, that words, suppose you take the word, let me think of a word. Let's take the word transformer itself. Transformer. You realize that actually the building blocks of these two words can be thought of as, where am I? This. One is trans, the other is former, because I can have, just to illustrate this point, I can have words like transfer, right? Transfer. Transfer, does it have S? Transfer, yes, of course it does. A transfer, transistor. And you can think of so many words that begin with TRA and S, isn't it? You can think of a lot of words, right? And likewise, former, you can think of reformer instead of transformer, right? Deformer, and God knows what other words you can cook up, but I'm sure you can cook up many other words that all have that. Are we together, guys? Right. So, and then you can further break the word former, and you can say it has a piece inside it, which is actually form, is the real building block, because form is there, reform, transform, just form, uniform, right? So on and so many pieces that you create. So people realize that it is better to take as building blocks for embedding, for tokens. When you convert words to tokens, take word pieces. Are we together? And there's a bit of technology to it. See, what happens is you first start with character level things. Let's say that you start with A all the way to Z. they have certain frequency. You see what their frequencies are. And suppose you create a frequency table, sorted it. Then you realize that if you have A, and if you do a combination of A and, well, okay, let me take this word form. Suppose you look at the word FO, right? Soon you realize that FORM, so suppose F is here, but it's in relative frequency sorted by decreasing frequency, means the most frequent characters at the top. Soon you realize that the word piece, FORM, or the word form, or just for, is far more frequent in text than just a F floating around. F floating around is a little hard to see in literature, right? So what happens is the form comes up, for comes up, right, and so on and so forth. There's a little bit more to it, and so what happens is that little word pieces, they begin to bubble up, right, in this, and you take them more seriously, right. And you take them as tokens. So suppose you want to pick the first 30,000 very popular tokens, right, or 10,000 very popular word pieces. It is better to take the 10,000, not the 10,000 most popular words, but 10,000 most popular word pieces, in the sense that each piece is in some sense information dense, right? And so you use some notation. You are saying, for example, if you say farmer, you can say I break it up into two tokens, form, and then you use a special thing to say and then er is the suffix, and er is the suffix to gazillions of things, and you treat this as this is a suffix notation. You're saying this is a suffix. So there's a little bit of a machinery here, a little bit of technical details, but those are not very important. But the important thing to realize is that it's a better idea to deal with word pieces as tokens. So the gist of all this discussion is to say that use word pieces as tokens. Tokens. It leads to much better results. So that is what they mean when they talk about using word piece. Where do they talk about that? Ablation studies and so forth. Fine tuning. Did I lose the place? Pre-training BERT, yes, we use word embedding, word piece embedding. So now you have word pieces, you can do the embedding of the word pieces, right? You use that. Then comes the embedding question itself. What form of embedding do we use? So far, we have said that you can, remember, we learned about word embedding. Now, when you use word embedding like word to whack or glove, they're a wonderful idea. I don't know if you were impressed or happy at the whole concept of word embeddings, the way it was done. I certainly was when I learned about it. But it has one limitation. It is context unaware. Because you have learned from the entire corpus of human language and you have just looked at the word vectors. Yes, you can do king minus queen is man minus woman and all sorts of beautiful relationship, but there is a problem. Homonyms, your words that in different contexts have different meaning, right? So for example, a transformer in AI means what we are talking about, isn't it? It's an architecture, neural architecture. But when you talk to an electrical engineer, a transformer is what hangs on the pole or in your neighborhood and does the voltage change, isn't it? From high tension, a very high voltage that is used for long distance transmission down to more residential area voltages. Are we getting the point, guys? That sometimes the word has many meanings. If you open the dictionary, you will see that a word can have many, many meanings. And each meaning is captured by the context where it appears, isn't it? For example, if you say the utility company had to purchase a lot of copper wires to go and repair the transformer, right? There, the meaning of transformer is entirely different than saying we used a transformer for sentiment analysis. Right? We certainly didn't use that big electrical device for sentiment analysis. right? So I hope that is an obvious thing that I'm saying. So then the question came, can we do a different embedding of words, which is context aware, right? So that work was happening along the way, and these people benefited. They said, yes, let us have context aware embedding of words, right? So I'll not dwell into that very much, just to mention the fact that that's what we eventually will use and do. So that is that. Now, next comes the actual embedding part. So I want to go over the architecture. Did they mention it here? I seem to be going. Okay, this paper is written in a very interesting way. It sort of talks about the results and its differentiation from other architectures before, quite a bit before it goes into the details. But I'll go to this picture. Are you guys able to see this picture here?
Yes.
On the left. So this needs a little bit of a description. You remember that in the classic transformer, you would take the word embedding plus the position embedding to make the final joint embedding of a word, right? Of a token. Do we remember that, guys? You take the token embedding, the word token, then you take the position embedding, but here we use one more thing, right? Which makes it interesting. And to illustrate what is meant here, what you do is typically think of two sentences. You don't feed it one sentence at a time. Let us, for reasons that we will understand in a little bit, think that for some reason it is doing, let me take a color, it is taking two sentences, S1, S2 together, right? So then the question is, how will it look? So traditionally it would have looked word 1, word 2 of the first sentence, right? Of the first sentence all the way to word, let's say N of the first sentence. Then you would put a demarcator, something called a separator, full stop, something that stands for the fact that you encountered a different, you're starting a new sentence, and then you would get W of the 2, so forth, W N of the 2 of the second one. So now there is one extra thing to do. So first of all, we need to distinguish whether you are in the first sentence or the second sentence, isn't it? It's a very basic thing. So that information is this layer, right? So for example, for the first sentence, it would say, okay, we are in the first sentence. We are in sentence A. Actually, since they use A and B, let me use AB. Sorry, I should have noticed that. They use A, and B, sentence B. I don't know if little bit you can see what I'm writing, this squiggly little thing, B, right? Two sentences, they're separated. So that's the first thing you do. So is position embedding easy to understand? This comes straight from your classic transformer that we did this week, right? The additional thing is this segment embedding. Segment, one easy way to think of segment is the sentence. Which sentence are you in, right? And the third is, of course, your classic word embedding. You take all of these three to create your complete embedding of this joint thing. But there is one extra thing you do. What you do is you prefix all of that with a new thing. You notice that. So this is like the beginning. This is saying is just the beginning. EA is not really a word. If you look at this sentence, my dog is cute. He likes playing. But before that, there is a pillar. There is a token to say it's the beginning of the word. And when it gets encoded, you deliberately call that particular token the CLS. Now, why CLS? That word looks rather cryptic. We'll talk about it in a moment. The reason for that will become evident in a few minutes. Right? But just say that you put, in the beginning, you put a token to specify that you're about to feed in this two sentences together. You just take two for the time being, but two sentences together. And then between the two sentences, you have the end separator, isn't it? And in the end also, so let me highlight the ones that you should pay attention to. This, and this. Do these make sense, guys? You basically get the encoding, whatever the embedding is, or total full encoding of the word "my dog is cute." Of course, those would by now be numbers. There'll be an array of numbers, typically 1024 or whatever it is, long array of numbers. And for each of these words, or word pieces rather, let's not use the word word. Do you notice a word piece here? If you observe this one, you see the word piece coming into play here, isn't it, guys? With the two hash saying it is a suffix. So that explains the hash marks, right? Uh, Actually, I should have given it another color so I could leave notes here. Let me call, what color am I left with? Maybe, let's take a little bit darker blue, different color blue. Right. Suffix as a word piece, right? So these are word pieces, word pieces encoded, fully encoded. So this is what will go into our transformer. Are we together, guys? So far? And you let it go into the transformer. If you have understood till this far, actually you have understood everything. There isn't much more to this paper. Ultimately, you'll produce a hidden state. This transformer architecture will, at the end of it, produce a hidden state, right? The output. And what you do is, let me actually write it here in this. So this thing goes in, let me say CLS, right? And the cow. By the way, is this blue visible, or is it hard to read at the bottom that I'm writing?
Okay.
Visible, right? The cow jumped over the moon. And then let us say there is a separator and there is another part that is going in. Actually, I should keep it horizontally there, but let me decrease the font size so I can stick more in here. The cow jumped over the moon, and then after that, we have another important thing. What else do cows do right after jumping over the moon?
Mood with delight.
Then she mooed with delight. Mood with delight, right? And then you have the separator, the end separator, right? You have the end separator here. So this is your separator here. So what happens is that all of these word blocks, and obviously these, I've written them as words, forgive me, but they're word pieces. So this would probably be jump and then hash, 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 ed or something like that. So I'll just leave it there, just being sloppy here, but we'll leave it there. So this goes in. Then what happens is you feed this into the transformer, the whole transformer architecture, the encoder part of it. What do you get? At the end of it, you get some output. The output that you get, and I believe they use the output of 124 dimensional out. This is your transformer, BERT transformer. BERT transformer, and then a hidden dimensional output for large, and I believe it's 768 dimensional output for base, which is comparable to in terms of parameters to GPT. So they just wanted to show that it's better, right? And also it's easier to use if you're working on modest hardware. So then comes the interesting thing. What do you do? So suppose you want to send it to a classifier. Say your task is sentiment analysis. And let us say that this has been pre-trained. Imagine a pre-trained BERT somehow magically, and we'll talk about how you have trained it. But imagine that this BERT has been just pre-trained. All the 340 million parameters in the large have some values, and those are sensible values for most tasks. So suppose you want to do sentiment analysis. What would you do? Let's say you put it through a sigmoid, either a sigmoid or a softmax, right? Whatever it is, you put it through and it will come back with positive or negative. Are we together? And now what do? You take a corpus of, you take an input data set, take, for example, the SST, whatever, take, or, movie review data set, take the movie review data set, for example, or whatever you want. This is a classification task. Classification or whatever. Your data is, what will it contain? It will contain sentences. And for each sentence, reviews. And it will contain positive or negative. Isn't it? So now remember that the definition of sentence has changed. The whole logical unit is they're treating it as a sentence, but that's all right. What you can do now is you can use this to fine tune or do final training, fine tune training of BERT. Right? In your particular problem, you put it together. All you have done is you have attached a softmax layer, let's say, and then you're saying, okay, I'm going to train it, except that you're not training from scratch. The parameters of BERT are already very close to the optimal. So your training will very quickly converge. And that kind of training, when you do transfer learning, is called fine tuning. So you have the fine tuning training of BERT and you're done. And then you can use it for many, many different tasks, but we'll come to that in a moment. But now let's ask yourself, that is all very lovely, that most of the parameters come almost near the correct answer for a large number of tasks. And all we have to do is screw in the last layer for whatever task we want to do. Right? But how in the world did we pre-train the BERT at all? So the pre-training of the BERT happens using two tricks. The task is, and that's what this paper talks about. And now we'll go into that. How is the BERT pre-trained? This is a crucial question, isn't it, guys? We are saying that BERT is so clever that most of its values, weights are already close to perfection for most, whatever task that you want to do. And all you have to do is a last mile training, a fine-tuning training, right? Then it begs the question that what is it that you do to make those magical weights or parameters to happen? Would you agree, guys, that that becomes a crucial question?
Yes.
Right. So now we will go to that question. So let's go to that question. How do you pre-train it? So the way you do, so fine tuning, of course, we understood. Let us go to the pre-training. So how do you pre-train BERT? You use two things, and this is just two particular approaches you use, and these are task one. Oh, sorry, this guy. Masked LMS, and the other is next sentence prediction. So let me talk about both. What you do is you give it in the task. So we'll talk about the masked LM, task one, masked LM. Task, you basically say go become good at, you say, go become good at these two tasks. Right? And what are those tasks? Task one, masked LM, masked language model. Masked language model. What you do is something pretty interesting. You take a sentence, right? let's say the sentence is the cow jumped over the moon in great delight. Right. I will take this. And you just go and nuke out some of the words. So one easy way to nuke out would be what? You just go and you say, well, suppose I remove this. So it becomes masked over the moon in, maybe I'll remove the word this also. But for the time being, let us just keep it simple and take one word that we nuked out. So I'll bring back the grateful just for simplicity. But generally, they are saying that empirically, they found that masking 15% of the words was quite effective in training this, in the training. Well, I'm writing in almost a curved way. All right, so you could mask 15% of these words in a given sentence, in the sentences that you fed to the machine, and that would be good enough. But we will say, again, I'll just give an example. Now our sentence becomes the cow, and then it becomes the token mask, right? And then the rest of the thing jumped over there. And remember, the first token is your CLS, right? Jumped over the, and then you say your end and so forth, separator, etc., right? And then what you do is you can feed it, and then you can feed another sentence with masks and so forth. Now you ask this BERT that go and produce. So what happens is that the final state, so I'll write it very simply, input. You give it the input with masks, and you will get an output. What you do is, see, now here is the thing. Each of these words will produce an output, a hidden state output, right? Because they are all going through the system separately. Do we remember? They will all have their K, V, attention and all of that. They are all going through this transformer in parallel, right? Except that, of course, there's a lot of self-attention happening between the words. They're looking at each other and asking, are you interesting, right? So at the end of it, they will all come up with some hidden state. Are we together? So this is the hidden state of CLS. Output state, this will be the hidden state of the word, hidden state of cow, and so on and so forth, and hidden state of separator, right? And then what you do is you pretty much throw away all the hidden states, and this is the crucial thing, and a very, very interesting idea. You only keep the hidden state that the beginning of the sequence has. And what happens is the beginning of the sequence, in some sense, has also looked over all the words, has been paying attention to all the words in the sequence, isn't it, guys? Right? Because every word is paying attention to all the other words. So as a convention, they wanted to pick one, and they picked up this special one, the first one, the beginning of that, the encoding, the hidden state produced by the first word. And what they do is, that is your hidden state vector, CLS vector, and that they feed into let's say a softmax. Softmax layer, what will it contain? Your entire vocabulary, right? So suppose your vocabulary has 30K. So the word pieces has 30K tokens of word pieces, right? Unique tokens. So what happens is that this softmax, how many nodes will it have? Guys? Right, 30K nodes, right? This is a softmax classifier. Am I making sense, guys? All I'm saying is you take the sentence, right? And you mask the one word and you feed it in, And whatever the output comes for the first word, you just feed it into a softmax classifier. And then you ask which word is it favoring, right? Whichever word, say softmax will end up favoring one word, the other words will be smaller, 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 right? So some word will be here. And you hope that the word that it favors is jumped, that once you train it well, in the beginning it will favor all sorts of random words, right? But gradually you compute the cross entropy error. So softmax, if you just as a reminder, the basic machine learning, when you do softmax or classification, you use what?
So, Asif,
Yeah.
so let's say the masked word that you put in your input is a noun. Wouldn't this mean that in the context of your sentence, it could also infer that the masked output would be somewhere else where there's another noun?
Yes, see what happens is by noun, I probably means, you don't mean the cow, horse, like a horse, a bird, or something like that. You probably mean a proper noun, like the name of an organization or something, a word that is relatively rare. Is that what you meant?
No, I mean, if the cow was the one that was masked, can it put the moon in the sentence, and then the cow would be the one that would be in the end as masked?
Okay, let me try to understand what you said. Suppose the sentence is the mask, or rather, since I'm using yellow for mask, the mask jumped over the mask, jumped, right? Separator, CLS. Now ask your question. I've masked out the cow. It's the noun. What is the question now?
So won't there be instances when it's paying self attention that it would predict it as the moon jumped over the and then mask?
No, it can't. All you have to do is fill in this word. No? The position, the word moon is already there in the sentence. So it could predict the moon jumped over the moon, right? But once you train it properly, hopefully it shouldn't predict that. Once it has been properly trained, it should probably pick cow or whatever it is, other things that habitually jump over the moon.
Oh, so the issue is only just a matter of training to be
Yeah,
able to get the right key.
exactly. That is the whole point, right? See, what happens is that how do you train? You make it produce random. So suppose this is totally untrained. So there are random weights sitting here, right? And then what happens is, so when you feed it to a softmax classifier, the first time around it will point to some absolutely absurd. For example, it may say the castle jump over the moon, right? Well, there would be a huge cross entropy loss coming from that mistake. No? Because you find that the word cow, which should have been there, its probability is extremely low. So very low probability. So let's take this example. Let's make it very literal, right? Suppose you take that cow, a probability of a cow turns out to be 10 to the minus 6 as an example, right? So what is the cross entropy loss? You remember the cross entropy loss is ln p of the cow. This was the right answer. What is the log of this? Well, you use natural log, but let me cheat a little bit and use base cheating, right? If it were base 10, then, so I'm cheating a little bit, you would be something like minus 6, isn't it? But your definition is minus. So minus of minus 6 is 6. So what you're saying is you're accumulating the loss over every of the data point being one sentence going in, a couple of, one sort of a sequence going in. So then what will happen? This has suddenly contributed a lot of positive loss to it. You need to minimize this loss. How will you minimize this loss? You will do the gradient descent, the backprop. Remember everything that we learned, right? The standard machinery of machine learning will kick in. So as you train it epoch after epoch, these weights will let me not use the word weights because they're biases also. Parameters will adjust to better values through backpropagation and gradient descent step. Are we together?
Yes.
Yes, Asif. I think my question would be, how does the mask, like, how does the mask affect that whole process? Let's say your mask was a noun in this context. How does having a mask, like, because I is that supposed to mean the mask supposed to mean it's a specific word that you were just hiding, or is
That
a
is it, a word piece. You're just hiding a word piece. And so your label data is literally this. This is your label data. And what is the word that you hit? Cow was the word that you hit. You ask this sentence, the classifier, to take this sequence, which is this entire sequence here, and the output, it should predict cow. So whichever word you hit, it should be able to predict that word. That's all.
Oh, okay, I see. So the mask is not like a placeholder for a noun in general. It's actually something you've already introduced before.
You just go in, pick a random word, and now that is the one that you're hiding. Mask means to hide. That is the one that you hide, and that is now the answer. You ask this. It's like a game you play with kids, right? You In school you must have gone through all these exams. They'll give you a fill in the blank, and in the blank they'll give you choices A, B, C, D, E, right? And they will see whether you can pick up the. Actually, maybe I should introduce this mask business in the quiz this week. I'll give you guys a lot of fill in the blanks and see if you can fill in the right word. Right? That is literally training the classifier. Right? Making BERT predict what was it that was hidden. What should have been there in the blank.
Like the hidden word is the labeled data.
It becomes the label data. So suppose you take a sentence, the cow jumped over the moon, and I take cow out randomly. You can pick any word you want. So suppose I pick cow. So what does it become? Cow becomes the target variable, isn't it? You expect BERT to read the masked sentence and somehow be smart enough to say, this mask should be, this fill in the blank, the blank has to be replaced with the word cow.
Okay, I see. In a way, this acts like how we do dropouts in neural networks, where we try to let the system catch up. That's sort of the same intuition.
See, dropout is a little bit similar. Dropout is for regularization. This one is just basically saying, I'm playing a game with you. I will hide a few words, and the whole thing you have to learn is you have to understand language enough to be able to put a sensible word here. So let's take a guess. Instead of cow, if it said the horse jumped over the moon, it would still be sensible, isn't it? But if it said the something very absurd, like for example, the hammer jumped over the moon. Hammers don't tend to jump on their own, right? Or something like that. Yeah.
Okay.
So then you would attach a penalty. You would say that, well, you know, this transformer hasn't quite understood the English language. After reading so many books, in other words, being trained in all these sentences, it has still not figured out that the most likely thing should be a cow and not a hammer. So then you train it some more. Are we getting the sense, guys?
Yes, yes. So this helps specify the language even into deeper detail by understanding
Exactly.
context.
Yeah.
Okay.
And so this is one of the ways. Actually, there is a little subtlety. There are some more things you do, but I don't want to go into that. When you mask this thing, where am I? Now it has again jumped. Okay, because I'm writing down here. So when you do this, you can, you mask it about 80% of the, so 15% of the tokens are masked. But even when you mask, quite often you mask it. Sometimes what you do is you replace it with a random token, right? And then, so anyway, actually don't go into it. Let's not go into that for the time being. Let's stick to the big ideas. The second thing you do, the second task is a pair of the sentences.
Asif sir, I
One second, let me just write it out first. Task number 2, sentences. Go ahead.
so I'm trying to understand this one where the masking, right? So we already have pre-trained model. The last layer
No, we
training
don't
layer.
have pre-trained, that's the point. We are talking about how to pre-train BERT.
Oh, I see.
Remember,
how to pre-train.
See,
Okay.
let me go back. I think you guys missed the whole point. I said that, see, if you have a pre-trained model, then fine-tuning it for a specific task is easy. But the big question that remains is how do you magically pre-train BERT in such a nice way that it can be used for so many tasks?
Right. Yeah, I forgot about that one. So if here when we are pre-training it for, say in this case, the label data says cow, but next time when there is blank, I mean there is a gap like this, the word is missing, will it understand the noun to be kept there, or like what will the model understand?
The beautiful thing is you don't even have to ask about the part of speech. In tuning this, right, because so many sentences have gone in, you don't even bother. It will figure out whatever word it points to will be a noun,
Okay.
right? But you don't have to just say pick from one of the nouns or something like that. You don't have to do any extra effort. It is smart enough to know at that moment.
Yeah, so that's my question. The word which it learns will be noun.
Yes, it will be. Yeah, it'll pick up the cow, right? So the second thing you do is you do this. You say that, and so let us read this because this needs a little. This may be worth reading it aloud. The second task, next sentence prediction. So suppose you take a long text and take a sentence and the next sentence, and now the two of them together becomes your input. The important question is, should that sentence follow the previous sentence? So in other words, should sentence 2 follow sentence 1? Does it make sense? Are we together? So I'll take an example. What you do is, and obviously here it makes sense. People found that it is better to pick these data from actual books, where there is a narrative, where there is a very good cohesion between the sentences. Don't just take random collection of words or sentences from somewhere, and that would not be the right way. So read books and Wikipedias. In fact, that's what they do. Google has a huge collection of books that it has read, right? A massive amount of books. And then it also has read Wikipedia. So you do the basic cleanup, you throw away the table of contents and headers and this and that from Wikipedia. You get to the core content where something is being described, right? So now suppose you have something like, you see, let's go back to our sentence. The cow jumped over the moon. And then what was the next sentence we wrote? It was in great delight, or something to that. We said, the cow jumped over the moon in great delight. Well, did we follow it up with some other sentence? I forget.
Then she moved with delight.
Oh, then she moved with delight. Okay. Then she moved with delight. Moved with delight. So these are two sentences. Huh? We can say that this one is sentence S1 and this one is sentence S2. Right. So this is valid, isn't it? Hopefully there is some book somebody has written where this sequence exists. So this is valid. So what you do is S1, S2, you say true. You have data like this. S1 followed by S2, you give it a score of 1, let's say, right? Or true, or whatever it is, or maybe true. Choose yours, just binary classification. And then what you do is, while S2 made sense, suppose I put S3 here is equal to something like that. And the derivative, or maybe something like that. The derivative of x cubed is 3x squared. Let's say that you find a sentence like that. So now this is a non-sequester, isn't it? S3 simply doesn't follow from S1, does it? Right? So what would you say that it is very unlikely that you'll find anywhere in the world a sentence like this. a combined sentence like this. Would you agree, guys?
Yes.
Right. So guys, make sure you understand this. This is a very basic thing I'm saying. I'm saying that you take valid pairs of sequences of sentences, A followed by B, S1 followed by S2, and you just pick up. You go through all the literature and you make some valid pairs, all the valid pairs. And then what you do is for each valid pair, also do this game. You take the S1 and replace it with S3 randomly chosen from somewhere else. Randomly chosen sentence. And let us hope that very, very rarely will it ever make sense after S1. So you give it a value 0. It says that no, this is not what it is. Are we together now? And so what you do is you create a lot of data. 50% are valid and 50% is invalid. So you end up really with a nice balanced data. And then once again, you can train this BERT. Are we together at this task, guys? And the weights will adjust. You ask it to somehow always tell the right answer. Does S2 follow S1 or not? Can it be trained, guys? It's just a classification task, right? A binary classification task.
Right.
Very simple. So when you train this, once again, the weights will go and get adjusted. All the weights and parameters, biases, they will all go and get adjusted everywhere. So at the end, that is it. That is all the pre-training of BERT, and that finishes a long journey. And it turns out that, and that's a sheer simplicity actually. They have not done very custom hacks for each of these tasks. They have done something fairly universal. They have trained it on masked sentences, and they have trained it on, sentence, the next sentence prediction, right? Task 1. Let me just summarize. Pre-train on task number 1, mask language model. In other words, be able to predict the mask. And number 2, next sentence prediction. And once you do that, it turns out that all your weights are pre-trained, and almost magically now you can apply a pre-train on. So now you have a shareable, in other words, you can downloadable general purpose transformer for various tasks. And once again, for each task, all that you have to do is do the fine tuning, right? So for each task,
tasks, right? It's all natural language processing tasks.
yes. So for each now, what you do is you, for each specific task, take the output. So the output of the BERT is always called the hidden output, just because, in the grand scheme of things, when you attach it to something else, BERT's output becomes hidden because it becomes the input to whatever it is that you're putting there. Take the hidden of the only one token, the CLS token output, the hidden. It's really the word people use, the word is hidden, but think of it as the output of BERT and feed it into your classifier, etc., etc. Whatever the task is, classifier, etc., etc. Whatever your task is, that is it, right? And that is what this paper is saying. That's all there is to this paper, right? It's a wonderful paper actually. At the end of it, it's remarkable that they've come up with this idea, and you can imagine how many experiments or how many things they must have tried before something like this worked. Right? Because it's not an idea that would easily occur on its own. A lot of trying this and trying that must have gone into it before they nailed down this fairly elegant general purpose architecture. So this is the architecture for BERT, guys.
Asif sir, can this be used as like a chat bot kind of thing?
Yes, chatbot is question answering, of course. Question answer is just one task.
Last layer tuning will be learning. I mean, training will.
It is very easy. All you do is you take the text. So you take the input text question. So whatever the user has asked, the text, right? Let's say in the chat, you're the customer service agent, whatever the user has put here, you feed it into your BERT, right? And it will point to the right answer, right? It will generate the right answer. So it will produce the answer, the appropriate answer. That's all.
Right. After like little bit of training.
So that is it. All these things that you think, 8 different tasks you see in this paper mentioned, this is it. Question answering is in that. You could train it now. So what it means is that you can take the pre-trained BERT and feed it into your specific problem just by adding a logistic regression or whatever it is. Why just logistic regression? If it chooses your fancy, throw in a SVM or whatever you want, and then jointly just train it.
So, sir, for training, how much data should suffice for
Remember, there are 2 trainings. No? BERT comes pre-trained.
Right.
That needs a ginormous amount of data. Like I said,
so that is already trained. One need not to worry about that part, right?
you need not worry about that. And then the second part, the fine tuning, that's the beauty of it, because you're just shaking the weights a little bit. You need very little data.
I see. So, sir, in the little data, like when you say, can we quantify like how
Depends
much?
on the problem. It depends on the problem. Let's say you're doing sentiment analysis. I mean, surely you would like to feed in a few thousand or tens of thousands of sentiments, right? Or something like that. So in deep learning world, right, numbers are a little bit large. The data sets are never like 30 data points or something like that to train.
I would assume, Asif, to Pradeep's question, if I were to train a chatbot that's going to answer questions typically from an FAQ collection that I already have, that FAQ corpus would be what I'm training on, right?
Exactly. Yes. Or fine tuning, or fine tuning on is the word you would use in the transformer language.
So you'll do both those things. One, kind of masking individual words and helping
No, you don't do that. No, Premjit. See, those guys, the creator, the pre-training of BERT has already done that. All the weights are there. When you do it, all you do is you put a softmax on top of it, pointing to the right answer. And BERT, you just do the fine tuning of it, which means that you don't play that game of task 1 and task 2, masked language model or the next sentence prediction. You don't do that. You solve your real problem. See, here's the thing. Suppose a question is asked. Think about it this way. A question is asked. Question. There are answers A1 to AN possible. Think of it. Is this not a simple classification task? Forget transformers and everything completely. This is a classification task, isn't it? Right? And question goes in and it has to point to some right answer. AJ, isn't it? That's all it is. And so what we are saying is this classification task you do with 2 steps. You put the pre-trained BERT, you don't touch it. You just put the BERT there. Except that you leave the weights to be fine-tuned, and then you put your normal classifier, put your softmax. Right? As an example, put your softmax. So the output of this goes into the softmax, and that output points to the right answer. And then what you do is you do a little bit, you take a bunch of table of data, Q1, A1, Q2, A2. You must be having some repository. Let's say, let's take an example for Oracle customer support, right? You have maintained a large database of questions, and what is the correct answer to those questions or text, right? You have that QN, AN. So what is this? You're just doing a prediction here, right? You can use this to fine-tune BERT. Fine-tune the model. So your model is not just BERT. Model is all of these things together, because here are the weights that go into the softmax. You're multiplying the BERT output with the weights, right? Fine-tune the model. which means fine tune the BERT weights and fine tune and tune the softmax weights.
Okay. So I think then in this understanding, the implicit assumption here would be we pick a BERT model that's already been done, let's say for the English language, and you use an English FAQ to complete this process.
Exactly. So whatever specific task you have, you fine tune BERT for that task. That's all in practice. So that is the whole value proposition. See, guys, I started out by saying that transformers take care of parallel processing, all right. But we needed a framework to have a highly shareable model, pre-trained models that you would apply to your problem and just do last mile fine tuning. Therefore, BERT is one very popular and powerful model like that.
So Asif, can you spell out a few constraints? Like when I try to summarize it, I said an English BERT, and then I'm using English FAQ.
That's not necessary. You can feed in English BERT and ask it to produce English questions and ask it to produce Hindi answers. Whatever you can do. I mean, see, those are not restrictions. Those things it's pretty clever at.
So what in essence what I'm hearing then is the fine tuning.
Yeah.
That amount of training is sufficient for BERT to be able to figure out the necessary learnings to go from one language to the other as well.
Oh, those things, translations and all of that. Those are very easy. Like that's the whole point, that it's surprising actually how powerful these transformers are. These have taken over the world practically in AI and natural language processing, right? They are the dominant theme. See, they are not perfect. Even today, if you go and try to translate something from Hindi to English, sometimes the translations are completely hilarious. I'll give you an example. Wo chakkar kha ke gir gaya. And then the English will come out, he ate circles and fell. You see that, right? So these things are not perfect. There are still a lot of limitations. Some of the translations can be still quite hilarious. But in a large number of situations, the translations are pretty good. Like, for example, let me put it this way. A friend of mine, he, for some reason, many years ago, he got a job in Huawei. Well, these days, it's not a good idea to take job in Huawei. Huawei used to have a center in Silicon Valley. He became one of their chief architects in one of their divisions. So he went there. Actually, you know him, Premjit.
Alex, right?
No, not Alex, Ram Veluri.
Yeah, Ram, okay.
So then everything, whenever he would be asked to go to China, all the symbols, the signs and everything was in Chinese. Occasionally you would see English, and it was very hard to figure out what was there. Just how do you go from place A to place B? And so he had this Android app. It would just do a translation. All he had to do is point it at a sign, and right away he saw the translation. So you can imagine that in practical life, it is very, very useful.
Now, what I'm trying to wrap my head around as I'm listening to all this is, if one has to think about an application context where one is looking at what is available commercially right now or in open source in terms of BERT, and then try to productize something, how much amount of effort is involved in that additional effort?
So generally, like when these things came out, and people don't realize that whatever effort you were putting in training your systems before these transformers came out, you're putting literally 1% of the effort now. People finish projects and go to market in many times, right? At least do a prototype presentation before clients in weeks now.
Okay.
And people are not used to the fact that these big transformer models are so versatile and they can actually do all sorts of things. So read the latest transformer that has come out is GPT-3. If you Google up, you will see there's so many videos. It just came out a couple of months ago. I believe in July it came out or something like that. Since then, people are still marveling at how many things it can do. Apparently, you tell it. One example somebody was showing. I hope I don't get it right. So let me see. What was he saying? They said that you can speak to it. You can give it a natural language description of a UI that create a user interface where a user can search through your inventory of books, let's say, or whatever items, and then be able to do this or that. And literally, GPT-3 came out with a fully formed um, user interface written in React.js, apparently,
Mm-hmm.
or JavaScript in HTML or something, right? Can you imagine that? We are there. I mean, the state of the art is so far ahead. Most people haven't woken up to the fact that AI has actually advanced that far, right? Nobody thinks that the AI can generate code for you. It is today. So, when you think of data visualization, for example, it is very tedious. You have data, you know what to do. You would sit down and write a ton of code, and then there'll be bugs and this and that, and so on and so forth. One of the things people are seriously looking at, and with some success, actually early success, I would say, but still fascinating results, is you talk to these transformers, and as you talk to it, it is literally getting into your data and drawing the visualizations in front of your eyes on the screen. Can you imagine that? So imagine what it does. I mean, when that new world comes about, what it does to the old historic reporting tools,
Mm.
right? It will completely put those on steroids, isn't it?
Asif,
Yes.
instead of training the words and sentences uh, with its like physically adjacent uh, peers, can we try to run like an attention model over like the whole thing on a summary, and then
Yes, you can do a lot of that. Dennis. See, here's the thing. That's a separate discussion. Today, I wanted to focus just on this paper. But okay, do one thing, guys. Look at this. Look at the sort of things you have, the things that they have dealt with, where they're getting the state-of-the-art model. So what are they trying it on? Let's look at this, right? Detailed experimental setup. So some of them, a Cora question pairs is a binary classification task. It will determine if two questions asked on Cora are semantically equivalent, right? Literally, search through it and then tell whether they're equivalent. It does it. A multi-genre natural language inference is a large-scale crowdsourced entailment classification task. Means if one sentence actually follows the other. Given a pair of sentences, the goal is to predict whether the second sentence is an entailment, contradiction, or neutral with respect to the first statement, right? Next is a QNLI, question natural language language inference, is a version of the Stanford QA database, which has been converted into a binary classification task. The positive examples are question sentence pairs, which do contain the correct answer, and the negative examples are question sentence for the same paragraph, which do not contain the correct answer. So you can do all of this. SSTs is the standard sentiment, of course, you're familiar with. COLA is the binary single sentence classification, where the goal is to predict whether an English sentence is linguistically acceptable or not, right? Means it makes sense or not, right? STB2, they all of these MRCP. Just read the wide variety of the data sets on which it was benchmarked. And just to think that in one fell swoop, a pre-trained BERT goes in, just think about it, what a breakthrough it is. In research, you get breakthrough improvements very, very slowly. You don't get this in one fell swoop. But look at this table. It seems to have in one fell swoop gone and done very well and beaten the state of the art in all these tasks, very different tasks. And that is why everybody woke up and said, my goodness, this is really a moment.
Asif, do you have any comment on the current software that's in the market for plagiarism detection? Do they work off similar models?
Yes. You have even the traditional string matching is pretty good, and then you put AI into the mix, and it becomes the whole thing runs on steroids. Very good. Actually, plagiarism is very fast, scalable, and reasonable, quite good at detecting. The question is the definition of plagiarism. That is the human element. Suppose two of my sentences match your book. At that moment, is it plagiarism, or is it that we independently had the same thought? There's nothing new under the sun. If I'm thinking of something, somebody else probably is also thinking something like that. And we might end up writing very common sentences. So where is the demarcation boundary of plagiarism? Does plagiarism start when you have at least a sufficiently large number of sentences which are essentially the same, or what is the definition? So you have to be a little careful with that. If you're over aggressive, like for example, some universities were, students were getting, very undergraduate students were getting pretty hurt. They were using some of these softwares, and they would submit a term paper, and immediately it would get flagged as plagiarism. And the students would swear that they had not plagiarized, and they wouldn't have known about those obscure references where something similar like that was written, right? So it is always there. Those tools have to be used with caution, but the machine can do it if you give up sufficiently good parameters. So for example, what's the likelihood that all a sequence of 100 sentences are exactly the same between you and somebody else? That probability is extremely low, isn't it? And you let the machine look into that, right? And then you train. I mean, see, you bring it. Plagiarism is a whole world in itself. So let's put it simply, it's very good.
Okay.
But by the way, I'm not an expert in plagiarism. I'm just saying off the top of my head, but I just happen to know broadly that they are getting pretty good results. I don't know all the details. So take it with a grain of salt on that front. All right, guys. So if that is it, if there are no more questions, I'll stop the recording.